Hello, my calculus students. Today we're going to cover 1.6, which is limit-based continuity. It's where we're finding functions that are continuous using limits. Okay, so for the function graph below, fill in the table with the given information. After filling the table, write 3 pieces of information that must be true in order for the function g of x to be continuous at x equaling a. So before we talked about continuity, for something to be a function to be continuous, it means that if I were to take my pencil along and trace this function, if I have to pick it up to continue on, that's where it's known as discontinuous. Okay, so this thing is discontinuous until it reaches the point -6, 5, and then after that, it's continuous until it reaches x equaling -3, then I have to jump over here and keep going, and then there's discontinuity here at x equaling 2, and then it continues on at just right of x equaling 2 until we get to x equaling 6, where it's discontinuous again, and then it continues to be continuous from 6 to 8. Then once it reaches x equaling 8, it then goes on forever being continuous. Okay, so what must be true is that f of a must be defined. If you notice here, for it to be continuous, there's a hole there. So f of a has to be defined. The second requirement means that the limit from the left and the right must be the same. Notice here on these values here, the limit from the left when x approaches -3 is 2, and the limit as x approaches -3 from the right is -4. So in order for this to be continuous, they have to be the same value from the limit from the left and the right. Okay, which in this case, there's a jump here. And the final requirement is that f of a must equal the limit of this. Okay, so the limit may exist at x equaling -6, but f of -6 isn't defined. Okay. And on top of it, it's not the same value as where the limit is too. So like for instance, this example here at x equaling 8, it is defined, like the limit is defined from the left and the right, it's -2, but f of 8 is -4. So that means that it's not continuous because there's a hole there. Okay, and so that's what these table of values are saying, is showing whether the function is continuous at a certain x value. So let's take an example, like for instance, when x equals -3. It says, is the function defined? If so, what is its value? So we look at where x equals -3, and that it's defined at this value here, and it's 2. Well, what's the limit from the left? Well, the limit from the left is 2. What's the limit from the right? Well, that's -4. Since those values are not equal to each other, since the limit from the left and the limit from the right are not the same, then it doesn't exist. Okay, the limit doesn't exist, thus it's not continuous. Okay, and so this table is just doing examples of showing whether or not the function is continuous at a certain x value. Okay. Now, once you've done that, we have to prove this with the 3-part definition of continuity. So the 3 parts of continuity are these guys up here. F of a is defined. The limit from the left and the right as x approaches a has to exist. And then f of a has to equal the limit as x approaches a. So the step 1 and 2 have to equal each other, and that's what step 3 is. Okay, so this is an extremely important definition in this class because it shows whether or not a function is continuous. Okay, and later on in the class, you're going to realize that in order for things to occur, functions have to be continuous on that interval. Okay, so here we have an example of g of -8. Is g of -8 defined? Is there a y value at x equaling -8? And there is. The value right here is at the value is up here, and that is at 4. Okay, so g of -8 is equal to 4. Now what we're going to show now is what the limit is at x equaling -8. So when we approach it from the left, it's going to be -5. When we approach it from the right, it's -5. So the limit exists at x approaching 8. But it doesn't hold for the third standard. The third standard says that g of -8 has to equal the limit as x approaches -8 of g of x. And that is not what's occurring. Okay? We know that 4 is not equal to -5. So therefore, g of x is not continuous at x equaling -8. You have to write those 3 steps to show whether or not a value is continuous. This is a big question that you will see on a free response question. And obviously there's a lot of application on multiple choice that deals with this. Let's go to x equaling -6. So if you look at x equaling -6, is there a value, a y value at -6? There is. That value is -7. As we, does the limit exist? So if we approach x equaling -6 from the left and we approach -6 from the right, does it exist? Yes, it does. It's the same value. It's -7. Well, since g of -6 is equal to limit as x approaches -6 of g of x, then g of x is continuous. Now let's go to the last one here, x equaling -4. So x equaling -4, it is defined. It's right here at -5. G of -4 is equal to -5. But let's see if the limit exists. Well, if we approach from the left, that value is -5. When we approach from the right, that value is -2. Since the limit from the left and the limit from the right are not the same value, we say that the limit doesn't exist. And since the limit doesn't exist, g of x is not continuous. So all 3 steps have to hold true in order for the function to be continuous at a specific x value. Okay. Now the next thing is using the 3-part definition of continuity to determine if the given functions are continuous at an indicated value of x. Okay. So what we're trying to show is we're showing, is the function continuous at -2. Okay, that should be a -2, not a -3. So if I plug a -2 into here, into the middle one, because that's where it's equal to, -2 is equal to that. So we plug it into the middle one. 3 times -2 is -6 plus 2 is -4. So it's defined. Now the question is, from the limit from the left, that's values that are less than -2. If we plug -2 in there, will it equal -4? Let's check. So if we plug -2 into here, 6 minus 2 is 4. The square root of 4 is 2. 2 times -2 is -4. But if we do the limit from the right, if we plug in a -2 into here, -2 pi is the same thing as just 2 pi. So that's equal to 1. 1 plus e to the 1 is, actually, 1 plus e to the -2 is the same thing as 1 over e squared plus 1. And so they're not the same. Obviously, -4 is not equal to 1 over e squared plus 1. So the limit doesn't exist. Right there and then, we say the function is not continuous at x equaling -2. This is common. You're going to see a lot of piecewise functions where you're going to have to apply the 3-part definition of continuity. So you'll see it here where at x equaling pi. So x equals pi at this value here. So if you plug pi in here, 3 pi over 4 is equal to -1. And then if we put a pi in for x here, e to the power of pi times -1 is -e to the pi. So that's the value. It's defined. Now we have to show, is that value true if we take the limit from the left and from the limit from the right? Well, what's nice about this is we already know the limit from the right. We just have to show that that is also true from the left. So if you plug pi in there, e to the pi times cosine of pi, which is -1. So it is. It's -e to the power of pi. So the limit does exist. Thus, since g of pi is equal to the limit as x approaches pi of g of x, then we say that g of x is continuous at x equaling pi. Okay. Now 6 is applying the same definition of the three-part definition of continuity, but this time finding our missing values of m and k. So you'll notice here that we have to set the limit from the left is equal to the limit from the right. So we set 2 equal to mx plus k, and then we set mx plus k equal to -2, because those values have to be the same, because in order for it to be defined at that value, it must hold true at -1. Well, then we also have to do that for this x equaling 3. So we have to show that the limit exists from both of these. So if we set this equal 2 equal to mx plus k, and we set mx plus k equal to -2, we have a system of equations where then we can solve for m and k. So you'll notice that I'm solving for m and k to find what values of k and m make this function continuous. I will definitely go through this example in class if you need any help with this. Okay, but notice that this guy right here goes to here, and this guy here goes to this. Okay. And then here's just another example, but this time it's with a system of equations where we have a little bit more complicated because we have a quadratic function and a linear function. So definitely something to look at in our notes, and then obviously jot down your questions that you have and complete the homework. And I look forward to helping you in class and answering your questions and going over this lesson. Have a wonderful day and talk to you soon.